So where we left off at the end of last class was going through different parts of the fork join pool. I had just finished telling you about what a common fork join pool was. And what I'm going to do now is talk about how to use something called a managed blocker to avoid starvation and to improve performance for the common fork join pool. Remember, the purpose of the common fork join pool was to have a single pool of threads that, of course, would be mapped to the underlying cores. And we wanted to do this in a way that would allow us to have all the different parts of the program that wanted to do parallel computing leverage a common pool. And the reason for having a common pool was it makes it easier for the underlying fork join pool to schedule the various work to be done, the chunks to be processed in a global way within a process. Now, when you do that, you end up having to use something called a managed, well, one way to be able to handle this is to use something called a managed blocker. So if you recall, the Java fork join pool is largely designed to work for tasks that so-called run to completion without blocking. And for certain compute-bound operations, like searching for keywords or phrases in the works of Shakespeare, something that's inherently embarrassingly parallel. Those are just good old-fashioned run-to-completion tasks. But there are certain kinds of tasks that don't run to completion without blocking. And what happens in those cases is you may need to be able to allocate more threads in the common fork join pool in order to keep the system moving forward, in order to make forward progress. And that's particularly true for blocking operations. If you recall, last time we talked about downloading images, which you'll get more experience with shortly when you do the next programming assignment. And in that case, when you're downloading an image, the thread that's doing the download from the remote website will undoubtedly block for a period of time. So what we need to do is have some way of being able to automatically and temporarily increase the size of the common fork join pool. And a good metaphor for this is sort of seasonal hiring. So there's certain places, Amazon perhaps, or your local shopping mall that hire people over the Christmas or holiday break, winter break, whatever you want to call it, where you want to be able to allow more people to come in and shop, and then you'll have seasonal workers that come in and help out, right? So it's not all the time, it's just seasonal. In fact, they actually do that at Vanderbilt when they have admissions period, when people submit their applications for review. They hire a bunch of sort of seasonal workers to review and read the admissions information. So what we do here is we have this way in the fork join pool of being able to reclaim threads that were spawned temporarily during periods of time when they're not being used. So we have a way of reaping them, as it's called. So you have like the Grim Reaper who will get rid of those threads and then perhaps be able to reinstate them later. And the idea of this is to be able to have some kind of automatic control feedback loop to ensure that we have the right number of threads that were requested by the user. So if the user says, I want 10 threads in my pool, or if the system by default says, I want 4 threads because I have 4 cores, then after the period where there's a burst of activity and the burstiness goes away, we want to allow things to shrink back to the default target level of parallelism. And the way this works is using something called a managed blocker. And there are a couple of methods in managed blocker. It's a very, very simple interface. And you can see here it's got 2 methods. One of them is called isReleasable. And this is a hook method. I'll talk more about what a hook method is in a second. It's a hook method that returns true if blocking is unnecessary. In other words, if whatever might have blocked didn't need to block because it got whatever it was looking for. Maybe it got a lock. Maybe it got a message or whatever. In that case, you say, hey, I might have had to have blocked, but I didn't block, so all is well. Then there's another method called block. And this method is what's going to be called back to handle the case where blocking actually may occur. And the kind of blocking we're going to take a look at, and I'll show you some examples of in just a second, is something like waiting for a lock or waiting for I/O to finish. So those are 2 examples of things that might block, or waiting for a message or something like that. And this returns true if no additional blocking is in fact necessary. In other words, if isReleasable would return true. It's actually somewhat rare for that to happen. It usually just goes ahead and blocks. But when it returns something, you'll know that it's now able to make forward progress. Here's how this ManagedBlocker mechanism is used internally by the fork join pool. So if we were to take a look at the fork join pool source code, which you can get if you were to follow this link, if you were to click on the link in the PDF slide, you would see that fork join pool extends abstract executor service. Don't worry too much about that. And it's got a method called ManagedBlock. And this method, which as you can see is a static method, is going to be used in a way I'll talk about in a second to activate a spare thread to increment the amount of parallelism while the calling thread is blocked. So it's kind of like you're working in a, trying to think of a good example. Let's say you go to a fast food restaurant to order something, and for some reason your order is taking longer than expected, so you have to work with the person you're doing the order with. So rather than make the rest of the line, sort of wait for you to finish whatever you're doing, it would be like the clerk you're working with would turn and say, hey, so-and-so, come up here and take the next customer. And so they would go off and handle you, and the next customer would get serviced by a newly created thread or a newly created worker. Obviously, creating threads is often easier than creating new workers, new people workers, depending on what environment you're in. So this is what ManagedBlock does. And what it'll do is it has this interesting method internally, which I'll just describe without going into the implementation details. It has this method called try-compensate. And what try-compensate does is it will go ahead and create or reactivate a spare thread to compensate for the blocking thread until the blocking thread or threads unblock. So try-compensate may spawn an extra thread to run in the background. And notice how in this loop is actually calling back to hook methods defined on the ManagedBlocker object passed as a parameter. So you will create the ManagedBlocker instance, and you will pass that into the ManagedBlock method, and then it will use hook methods like isReleasable and block in order to call back to the code that you wrote. That's really all a hook method is. It's just a way to call back to something and get some user-defined behavior, some application-defined behavior. So this call here may, in fact, block the calling thread. And if it does, we're OK, because try-compensate will end up spawning a thread in that case, a new thread. So let's take a look at a couple of examples to see how this works. Yes, question? This call to block, as we'll see in the next couple of examples, will in fact block the calling thread. That's correct. And so that's why all this machinery is needed by the fork join pool to create these extra threads to handle the case where another thread or other threads will block. So again, what you're trying to do is you're saying, while one thread is busy waiting on a customer, another thread will be created to handle new customers so that there still are ways of handling the customers. That's the way to think about it. So here's some examples. These examples actually come right out of the Java docs for the ManagedBlocker class. I'll just walk through and explain them in a little bit more thorough way than if you looked at the documentation. So here's a class that we might define called ManagedLocker. And ManagedLocker implements ManagedBlocker, because ManagedBlocker is an interface. And this is going to be used to handle a blocking synchronizer. So as you can see here, we've got a ReentrantLock, which is going to be passed in as a parameter. And the constructor stores the lock in a private field. We've also got a flag that keeps track of whether something has been acquired or not. IsReleasable, this is kind of clever. What it does is first it checks to see whether this flag has already been set to true. If it has been set to true, we don't have to block. If it hasn't been set to true, it attempts to try to acquire the lock without blocking. And I won't go into this in too much detail, but the synchronizers that are available in Java, at least for things like ReentrantLock, which is a mutual exclusion mechanism, basically have these non-blocking methods. And try-lock is an example of a non-blocking method. And what it tries to do is it tries to get the lock. If the lock is available, then it grabs it and returns true. If the lock is not available, if someone else already owns it, then what try-lock does, it just returns false without blocking. So it's a non-blocking lock acquisition mechanism. It's kind of like if you've flown in an airplane in the last 20 years or whatever, ever since 9/11, they don't like you to congregate by the restroom at the front of the plane, right? You can't queue up there. So think of try lock as kind of like that, right? What you do is actually the easiest way to do it is just look up, because there's usually a little sign that says occupied or vacant. But let's say that sign was broken. You would walk up, you need to use the restroom, you walk up to the door, you try to go in it, it's locked because somebody's in there, it's occupied. So rather than queuing up and blocking, you have to go back to your seat, right? So that's kind of what try lock is like, right? It's trying to get the lock. And if you can't get it, it's okay. You'll just do something else for you, read a newspaper or whatever. So that's what try lock is trying to do. And it's just trying to see whether we get lucky and get that lock. If it doesn't work, then we're going to have to block. And so this comes back to your question from a second ago. So if we don't already have the lock, then we call mlock.lock. That one actually blocks, right? That's kind of like going to the restroom at the back of the plane where you can stand in line. So here you're just going to wait your turn until you get the lock. So block will actually block, and that's why the fork join pool has all this stuff, like the try compensate, to handle the case where block actually blocks. If we get lucky, we don't have to block, but if we do have to block, then this extra thread will have been created to help us out. So that's blocking on some type of synchronizer. That's sort of the flow of using these things. Here's how you might handle it if you're trying to block on some kind of input mechanism. In this particular case, we're trying to get something out of a blocking queue, which is kind of an input mechanism, sort of. You're trying to input something from a queue. How about that? So we have something called queue taker, which implements ManagedBlocker, and it'll handle a blocking queue. What's a blocking queue? A blocking queue is just a queue where if the queue is empty, anybody who wants an element from the queue has to wait till there's an element. If the queue is full, anybody who wants to put something in the queue has to wait till the queue is not full. That's what a blocking queue is. There's a bunch of blocking queues in Java. There's a linked blocking queue, there's an array blocking queue, and so on. So down here, we initialize MQ, which is the private field, or the package private field to be whatever the parameter is releasable, attempts to do a non-blocking acquisition of an element from the queue. So poll is a method that will simply return the item if there is one, and if there isn't one, it'll just return null. So poll is a non-blocking way of trying to get something out of a queue. So if we're lucky, we get it. Otherwise, we call block. As you can see, what block does is it calls mq.take, and mq.take will, in fact, block until there's something in the queue. So it'll block until an item is actually available. So that's a blocking call. And if you're going to do something like this, then you need some way of getting the element that came out of here, which is what getItem is going to do. So after ManagedBlock returns, then we can extract whatever element was taken while we were blocked. Of course, it'll also work if we were able to get lucky and isReleasable worked, but we'll end up with an item in either case. All right, so that's kind of the mechanism. Now let's take a look at how we can encapsulate this mechanism with something even cooler. And you'll get to use this, or this will be used in the next assignment you'll be doing. So what we're doing here is we're wrapping a little class, a little helper class, around the ManagedBlocker so we can work with ManagedBlockers in a more intuitive way. And the BlockingTask class is going to be used to integrate suppliers. I'll show you an example of a supplier in a second. Remember, supplier is one of those functional interfaces we learned about with Java 8. So we can use a supplier with the common fork join pool. And this will give us a much cleaner, cooler interface than we otherwise would have, because it hides some of the complexity. So here's the class BlockingTask. Here's the method. It's a static method. Call in ManagedBlocker. So the call in ManagedBlocker method will be passed a supplier, and it allows you to pass suppliers, which are just lambdas or method references, to use them with the common Java fork join thread pool. And you'll see when I show you the use case here, it's really clean, really simple way to do all this stuff, and it hides all the details. Here's what we do. We take the supplier that's passed in, and we encapsulate it in an internal helper class called supplier ManagedBlocker, and I'll show you what that looks like in a second. And so we encapsulate the supplier within this supplier ManagedBlocker. We then say, hey, fork join pool, go ahead and let me know when this thing has finished. So we pass the ManagedBlocker object into this. and that'll block or not. I mean, it'll do something till it gets what we want. And then when we're done, we return the result that came back, which will include whatever the supplier was trying to do. All right, so that's the high-level view of this. Let's take a look at what is happening under the hood. Supplier ManagedBlocker, which is this helper class we looked at here. This is the one that's the encapsulation class. This implements fork join pool ManagedBlocker. So this thing can be called here to pass the ManagedBlocker in. And it's got a bunch of little fields. It keeps track of, like, the supplier, keeps track of whether it's done, keeps track of the result, and so on and so forth. And what it'll do is it'll take the supplier that was passed in over here, and it'll stash it away into a private field. Here's the block method. The block method will say, hey, supplier, get me whatever you want. And that's the cool part of this. Suppliers have a get method, if you recall. You can pass a lambda expression or a method reference in here, and so this will simply go ahead and do whatever you told it to do in the context of the ManagedBlocker mechanism that the fork join pool knows about. So this will go ahead and block, and it'll store the result. Is releasable, we'll just return whether or not we're done. We're probably not done for the most part, but it'll go ahead and return it if it is done. And then get result simply returns the result that was stashed away by the call to get up here. Okay, so now let's see how this thing actually gets used. So what we're going to do is I'm going to show you a little snippet of code from one of my example applications in my GitHub folder. And it'll use the blocking task to ensure there are enough pools enough threads in the common fork join pool in order to do blocking I/O operations. So that's where we're headed with all this stuff. So we have a method here called blocking download. And blocking download is going to take a URL to some image out there in the internet or the web somewhere. And it's going to transform that URL into some kind of image object, which just keeps track of the data that was downloaded, the JPEG or the PNG or the GIF or whatnot. It'll transform the URL to an image by downloading each image using the URL to get to it, which could block, right? That could be a long-running operation. So all we have to do here, this is really cool. We simply say, let's assume that there's another method called downloadImage, which does the downloading. Don't worry about the details. It's just going to go out, open a connection to that URL, and then suck it down, suck the contents down. So downloadImage on the URL, that's just a good old-fashioned lambda expression. We're just saying, download the image, except we're going to call this thing in the context of BlockingTask.call in ManagedBlocker. So this will ensure that the common fork join thread pool is expanded to handle the blocking image download. So all we have to do is just give it a supplier. This is just the supplier lambda, right? That's just the download image. That's what's actually going to be used when the get method is called here. When supplier.get is called, that will end up triggering this supplier lambda that was given here. So once again, the beauty of Java 8 functional programming is it makes it real easy to pass in some supplier lambda, and then we wrap it up in such a way that we can use it inside of other portions of Java, like the ManagedBlocker. Now, obviously, if we have a bursty period where we download a bunch of images and then we do a bunch of other stuff and so on, there'll be a time when we need to expand the number of threads in the fork join pool. But then later, those threads can be shut down and terminated because they aren't going to be needed. So it'll bring it back to the target parallelism level by reaping the unneeded threads if they're not used. The one potential downside with this model is that you can end up saturating the CPU cores during bursty workloads. So if it turns out that, all of a sudden there's 2,000 images to download, this type of approach will end up making a huge number of threads in the common fork join pool for that bursty period. So you could end up, for that period, sort of pegging the CPU, which may or may not be a bad thing. I mean, it's not the end of the world usually. That's why CPUs exist. They're meant to run, right? They're kind of happiest if they're doing something useful, right? It's like trying to think of an animal like a sheepdog, right? It's not happy unless it's hurting something, right? But the same thing is true with the CPU. You just have to be aware that this particular approach will potentially grow without bound during bursty periods. There are, of course, ways to throttle back on that if you wanted to, but this particular approach is best if you don't have huge numbers of clients sending requests during a bursty time. Okay, so that is the end. Now we're officially and formally done with the fork join pool stuff, and you should have enough information, you actually have more than enough information, in order to be able to start assignment 2, which will come out shortly.